In Euclid's Elements, there are 5 common notions that get used in proofs, but the first 3 are going to get used in this video. Common notion 1 says things which equal the same thing equal one another. It's kind of like saying if you have 3 people, A, B, and C, and if you said A and B have the same, A and B have the same height, I'll say same height. And then we also compare B and C to each other, and we find that B and C have the same height. We don't have to compare A and C, because if A and B have the same height and B and C have the same height, then A and C have the same height also. So we can say like A equals B, B equals C, and the conclusion is that A equals C, because the things equal the same thing. They both equal B. We don't call it common notion 1 anymore. Instead, we call it the transitive property. Common notion 2 says if equals added to equals and the wholes are equal. That's like saying here's 2 people, and they both have $50. And then I give each of them, so they have equal amounts of money to begin with. And then I give them equal amounts of money. And now the amount they have is still equal. So equals added to equals, the wholes are equal. This is going to be called the addition property. And finally, if I take those same 2 people that each had $50, and instead I were to take $10 from each of them, now they would have $40, and they would both have $40. They would be the same. This common notion 3 is for us going to be called the Now, some people throw in extra words like the transitive property of equality, addition property of equality, subtraction property of equality, and then sometimes they're talking about congruence if it's line segments, not numbers, like the transitive property of congruence, the addition property of congruence, subtraction property of congruence. But you can just write from me, transitive property, addition property, subtraction property. So here is sort of the most typical question that involves one of these postulates. We have here some given information. And the first one says that AB is congruent to DE. So in the picture, I can go like that. I'm even going to make it red. So those line segments are given as congruent. And we're also given that BC is congruent to EF, so we can make little 2 marks like that. Now, it might seem pretty obvious that the big line segment, AC, has to equal the big line segment, DF. And that is going to be the conclusion. The reason is going to be the addition property. Now, I'm going to not want you to jump straight to saying AC is congruent to DF. Instead, since we're using the addition property, this is what I want you to write, this thing over here. Basically, if you're going to use addition property, I want to see that there's already 2 expressions that have, in this case, a congruence between them, and that we literally added one side, in this case AB, to one of the other sides, one of the sides of the other one, which is BC. That's AB plus BC. And then that's congruent to DE plus EF. I want to see this. Some books don't. Some books jump straight to this conclusion. But to me, addition property, we need to see some pluses. And that's the way I want you to do this question. Now look at this picture. Here I have angles. And the given information is that HGI, we name an angle through 3 points with the vertex being in the middle. So HGI, which is this angle, is congruent to LKM, which I mark that way. It's also true that IGJ, which is this smaller angle, you make two arcs, is congruent to MKN. Now, the conclusion is going to be that the full angle, which I'm going to actually just trace the full angle for now. Let's see, I'll use this color. This full angle is congruent to this full angle. I could make, I'm drawing this in as like the goal is to prove that. We haven't actually proved it, so I shouldn't be writing it in just yet. In fact, let me get rid of those. You only make those markings once we've actually done the proof. So for this one, we are going to use the addition postulate again, or the addition property. And what we write is, anytime you do the addition property, we need to actually add some things together. So if I add together these two sort of congruences, it's HGI plus IGJ is congruent to LKM plus MKN. But I'm going to write this comma, just like I did in the last one, and the word or, and then I'm going to combine those because HGI and IGJ, they're adjacent angles because they share the IG side, so I can actually combine them. And that was our goal. Our goal was to actually say this, but I'm having you first say something like this, because if you're going to use addition property, I do want to see some plus signs, and I want to see clearly which two things got added together. Now this picture is pretty much, it's the same picture as we had in the first example. But this question is a little bit different because in this one, notice the given information is that AC, which is the entire line segment, is congruent to DF. So it's a little confusing because of the way that this line segment's composed of the other two. So I kind of make this little curly braces thing and put a mark on it to say those are equal. And I also am given that BC is congruent to EF. And the conclusion we'll eventually get to is that the other piece, BC, is congruent to DE. But the way we get there is by using the subtraction property. And the way the subtraction property works is we take these two statements that both have congruence in them, and we literally subtract them. And when I do that, I don't jump yet to AB is congruent to DE, but just that AC minus BC is congruent to DF minus EF. That's really what you can say with the subtraction property, but I'm going to now let you jump to the sort of conclusion because AC minus BC is AB, and DF minus EF is DE, so we could say that also. And that's how the subtraction property gets used. Now, this fourth question looks a lot like the second one, except the given is that the full HGJ, this full angle is congruent to LKN, which is the full angle. And also IGJ, which is this little piece, is congruent to MKN, which is this piece. And the conclusion eventually is going to be that the other piece, the MKL piece, is going to be the same. If you imagine these as like slices of apple pie, if the big piece was originally equal and you cut off a sliver from each of them, the remaining piece will be equal also. So for this one, it's going to involve subtraction. subtraction property, because you're going to be subtracting these two things. And when you do that, it looks like this. That's the subtraction property. Some people say subtraction property of congruence. But I'm going to let you then just jump to an equivalent statement. So you can write or, and then you can say that. So we're basically, if I make this green, now we're able to conclude that this angle here is equal, congruent to that angle there. Now in this question, we only have one given statement, and there's only one big line segment. AB is congruent to CD, so whoops. That's thicker than I had meant it to be. Okay. So AB, which is this line segment, is the same length as CD, which is that line segment. So the thing we're going to be able to eventually say is if I add the line segment BC to both of these things, then this bigger line segment, AC and BD, should be congruent also. It's kind of like if AB and CD were both 2 inches long and BC was 5 inches long, then AC would be 7 and BD would also be 7. Now, eventually, we are going to use the addition property. And eventually, we're going to say that AC is congruent to BD. But what goes in between is a little bit unusual. Because BC is the thing that got added to both things, you're going to actually have to say BC is congruent to BC, and that's called the reflexive property. Now that I have two congruences, I can add them together to use the addition property, and that's why this thing here is AB plus BC is congruent to CD plus BC, which is also a way of saying AC is congruent to BD. As sort of unusual as this step might seem, and some books don't even force you to use it, but I think on the Regents they want that. I wanted to see it on my test, because if you're going to use addition, I need to see pluses, and if this line 2 wasn't there, what would I be adding? So you have to say they're equal so that we can add these two lines together. Someone might argue that even without line 2, it would be okay to say AB plus BC equals CZ plus BC, because it's obvious that BC is equal to itself, or we're adding the same thing to both sides, but this is how we're going to do it. This also works for angles. If I'm telling you that HGI, I'll make this one red. HGI is this piece, is congruent to KGJ, which is that piece. And you'll notice that this piece in the middle, IGJ, it's kind of bordering both angles. So what happens in this one is that if we say IGJ equals IGJ by reflexive, then I can add these two congruences together and say HGI plus IGJ equals KGI plus IGJ, or these bigger angles. So, and I should also mention, because I didn't over here, when you use reflexive, it's a good practice to mark it, and I mark it like an X. That's saying that I'm going to use, that I used reflexive. Same thing over here. I might go like this, 2 arcs, and like an X on it. It's just telling me that I was using reflexive. But we ended up proving that this angle is congruent to this angle. They overlap. In this one, it has just one line. So from A all the way to C, whatever that is congruent from B all the way to D. That's the given. Now, for this one, you see how they overlap at BC? So if I say BC is congruent to, BC, which I will mark up by going like that, then I am able to subtract AC minus BC is congruent to BD minus BC. That's subtraction property. Oh, and I used reflexive property there. But what is AC minus BC? Well, when you take BC away from AC, what remains is just AB. And when you subtract BD minus BC, you end up with CD. So it takes a little practice sometimes to be able to see this. But that's what we prove. And in this one, the given is that HGJ, which is this angle, is congruent to this angle. And you can see they have this overlapping portion in the middle. So the trick is going to be to say that middle part is congruent to itself. And then when you subtract them away from both sides, so we say the middle part's congruent to itself by reflexive. Then when you subtract that middle part from each of those sort of medium-sized angles, we get HGI minus IGJ equals KGI minus IGJ, and that's also a way of saying KGJ equals IGH. So subtraction property got used in that one. And we end up proving, that this angle here is congruent to that angle there. If you're having trouble understanding this or thinking about it, I think if I gave you this picture, and I get rid of all this, and I gave you like specific information, like I said that this angle here was 70 degrees, and that, I'll use a different color, this angle here was also 70 degrees. And then I also gave you a third piece of information that the angle in the middle there that's shared by both was 50 degrees. I don't think you'd have so much trouble concluding that this is 20 and so is that. But in a similar way, even if I don't tell you what the specific measures are, if the big angle if the big angles are equal, the green one there and the maroon one, of course the angle in the middle is equal. So when you subtract equals from equals, whatever they are, the result will be equal.